Okay, तो वेव ऑप्टिक्स पढ़ते हैं। टोटल 17 पेजेस का चैप्टर था आएगा जिसमें मैंने भी थोड़ी देर पहले देखा था। Introduction. Wave optics. Introduction. In 1637, Descartes gave the corpuscular model of light and derived Snell's law. It explained the laws of reflection and refraction of light at an interference. The corpuscular model predicted that if the ray of light on reflection bends towards the normal, then the speed of light would be greater in second medium. If this corpuscular model of light was further developed by Isaac Newton in his famous book called Opticus, and because of the tremendous popularity of this book, corpuscular model is very often attributed to Newton. I guess ये introduction वाले part की जरूरत पड़ लेते हैं. In 1968, Dutch physicist Christian Huygens put forward the wave theory of light. It is this wave theory model of light that we will discuss in this chapter, and we will see the wave model could satisfactorily explain the phenomena of reflection and refraction. However, it predicted that on refraction, if the wave bends towards the normal, then speed of light would be less in second medium. This is the contradiction to the prediction made by using corpuscular model of light. It was much later confirmed by experiment where it was shown that the speed of light in water is less than the speed of light in air, confirming the prediction of wave model. Foucault carried out this experiment in 1850. Wave theory was not readily accepted primarily because of Newton's authority, also because light could travel through vacuum, and it was felt that wave could always require a medium to propagate from one point to the other. However, when Thomas Young performed his famous interference experiment in 1801, it was firmly established that light is indeed a wave phenomena. The wavefront of visible light was measured and found to be extremely small. For example, the wavelength of yellow light is about zero point 0.6 micrometer. Because of the smallness of wavelength of visible light, the comparison to the dimensions of typical mirror and lenses, in comparison to the typical mirrors and lenses, light can be assumed to be automatically traveling in straight lines. This is the field of geometrical optics, which we had discussed in the previous chapter. Indeed, the branch of optics in which one completely neglects the finiteness of wavelength is called geometrical optics, and a ray is defined as a path of energy propagation in the limit of wavelength tending to zero. After the interference experiment of Young in 1801 and first 40 years or so, many experiments were carried out involving the interference and diffraction of light waves. These experiments could only be satisfactorily explained by assuming a wave model of light. Thus, around middle of 19th century, the wave theory seemed to be very well established. The only major difficulty was that since it was thought that a wave required a medium for its propagation, however, how could light wave propagate through vacuum? This was explained when Maxwell put forward the famous electromagnetic theory of light. Maxwell had developed a set of equations describing the laws of electricity and magnetism. And using these equations, he derived what is known as wave function. Wave equation from कहाँ गया? Wave using these equations, he derived the known wave equation from which he predicted the existence of electromagnetic waves. From the wave theory, Maxwell could calculate the speed of EM waves in free space, and he found that the theoretical values were very close to the measured value of speed of light. From this, he propounded that light must be an electromagnetic wave. Thus, according to Maxwell, light waves are associated with changing electric and magnetic field. Changing electric field produces a time and space varying magnetic field, and changing magnetic field produces a time and space varying electric field. The changing electric and magnetic fields result in the propagation of electromagnetic waves or light waves, even in vacuum. In this chapter, we will first discuss original formulation of Huygens principle and derive the laws of reflection and refraction. In the section 10.4 and 10.5, we will discuss the phenomena of interference, which is based on the principle of superposition. In section 10.6, कहीं पढ़े हैं अभी आगे आगे सबके हाँ Huygens principle 10.2. We would first define wavefront. When we drop a small stone on a calm pool of water, waves spread out from the point of impact. Every point on the surface starts oscillating with time. At any instant, a photograph of the surface would show circular rings in which the disturbance is maximum. Clearly, all points on such a circle are oscillating in phase because they are at the same distance from the source. Such a locus of point which oscillates in a phase is called wavefront. Thus, a wavefront is defined as a surface of constant phase. The speed with which the wavefront move outward from the source is known as speed of wave. This energy of the wave travels in the direction perpendicular to the wavefront. If we have a point source emitting wave uniformly in all directions, then locus of the point which have same amplitude, and vibration in the same phase as spheres, and we have what is known as spherical wave, as shown in figure 10.1 given. At a large distance from the source, a small portion of sphere can be considered as a plane, and we have know it as a plane wavefront given. ठीक है. Now, if we know the shape of the wavefront at t is equals to 0, then Huygens principle allow us to determine the shape of the wavefront at a later time tau. Thus, Huygens principle is essentially a geometrical construction which, given the shape of the wavefront at any times, allow us to determine the shape of the wavefront at a later time. Let us consider diverging waves. Let F1, F2 represent the portion of spherical wavefront at t is equals to 0. Now, according to Huygens principle, each point of the wavefront is the source of secondary disturbance, and wavelets emitting from these points spread out in all the directions with the speed of the wave. These wavelets emitting from the wavefront are usually referred to as secondary wavelets. And if we draw common tangents to all these spheres, we obtain a new position for the wavefront. पहले यहाँ से और निकली तो यहाँ पे और भी बने स्फेयर और एक और wavefront. Thus, if we wish to determine the shape of the wavefront at t tau, we draw the sphere of the radius v tau from each point of the spherical wavefront, where v represents the speed of the wave in the medium. If we now draw a common tangent to all these spheres, we obtain a new position of the wavefront at t is equal to tau. क्या कर रहा है यार ये? छोड़ो. The new wavefront is shown as G1 G2 in figure 10.2 is again spherical with with point O as the center. The above model has one shortcoming. We also have a back wave which which is shown by D1 D2 in figure 10.2. Eugen argued that the amplitude of the secondary wavelet is maximum in the forward direction and zero in the backward direction. By making this ADHO's ad hoc assumption, Eugen could explain the absence of backwave. However, this ad hoc assumption is not satisfactory, and the absence of backwave is really justified from more vigorous wave theory. In a similar manner, we can use Eugen's principle to determine the shape of the wavefront for a plane wave propagating through a medium. ये वही यूजन वाला बनाया हुआ. Refraction and reflection of plane waves using Eugen's principle. Refraction of a plane wave. ठीक है. We will now use Eugen's principle to derive the laws of refraction. Let P dash represent the surface separating medium 1 and medium 2 as shown in figure 10.4. Let V1 and V2 represent the speed of light in medium 1 and medium 2 respectively. We assume a plane wavefront AB propagating in the direction A dash A incident on the interface at an angle I as shown in the figure. Let tau be the time taken by wavefront to travel a distance bc. Thus bc is equal to v1 tau. मतलब कि ये है v1 tau और ये वाला हो जाएगा v2 tau और यहाँ पे आके वेवफ्रंट ऐसा बन जाएगा ये ग्रीन वाला. कलर चेंज कर लेता हूँ. रेड मोड. ऑल राइट. In order to determine the shape of the refracted wavefront, we draw a sphere of radius v2 tau from the point A and in the second medium. The spread of the wave in the second medium is v2. The speed of the wave in the second medium is v2. Let CE represent the tangent plane drawn from point C on the sphere. Then AE is equal to v2 or v2t. AE C कहाँ है? C ये रहा. Okay. And CE would represent the refracted wavefront. If we now consider triangle ABC, अरे proportionality prove करी हुई है सारी और ये laws of refraction आए हैं. ये सारा मैं proofs नहीं पढ़ रहा. क्रिस्टियन यूजन, ये देखो यूजन, यार साइंटिस्ट है. From the above equation, we get this important result that is R is less than I, that is refracted angle is less than incident angle. That is, if the ray bends towards the normal, the speed of the light wave in the second medium V2 will be less than the speed of light wave in the first medium. This prediction is opposite to the prediction from the corpuscular model and as later experiments showed, the prediction N1 is equal to C by V1 and N2 is equal to C by V2 as known are known as the refracted indices of medium 1 and medium 2 respectively. In terms of refractive indices, equation 10.3 can be written as N1 sin 1 is equal to N2 sin N1 sin I is equal to N2 sin R. This is the Snell's law of refraction. Further, if lambda 1 and lambda 2 donate the wavelength of light in medium 1 and medium 2 respectively, and if the distance BC is equal to lambda 1, then the distance AE will be equal to lambda 2. Because if the crest of B have reached C in time tau, then crest of A should also reach to point E by in time tau. Thus, lambda 1 by lambda 2 is equal to BC by BE is equal to V1 by V2. Or V1 by V2 or V1 by lambda 1 is equal to V2 by lambda 2. The above equation implies that when the wave gets refracted into a denser medium, V1 is greater than V2, the wavelength and the speed of the propagation decreases, but the frequency nu, that is V by lambda, remains same. Cool. Refraction at rarer medium. मतलब पहले हम गए डेंस से रेयर, अब हम जाएंगे रेयर से। हाँ। Now consider refraction of plane wave at a rarest medium. That is, V2 is greater than V1. Proceeding in an exactly similar manner, we can construct ये सारा proof नहीं पढ़ रहा अभी मैं, इसकी जरूरत भी नहीं है शायद, रेफरेंस के बारे में तो पता ही है। यहाँ पे टोटल इंटरनल रिफ्लेक्शन के बारे में आ गया बीच में, जब आई इतना ज़्यादा हो जाएगा कि ये घूमते 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 यहाँ पे यहाँ ही पहुँच जाएगा। जिंदर में इतने यहाँ से यहाँ पहुँचा, अंदर में ये यहाँ से यहाँ पहुँच गया। रिफ्लेक्शन ऑफ अ प्लेन वेव, रिफ्लेक्शन ऑफ प्लेन वेव, ये पहले भी नहीं पढ़ रहा था ना, यहाँ से पढ़ लेता हूँ। Once we have the laws of reflection and diffraction, the behavior of prism, lenses, mirror can be understood. These phenomena were discussed in detail in chapter 9 on the basis of rectilinear propagation of light. Here we just describe the behavior of the wavefronts as they undergo reflection and or refraction. In figure 10.7, we consider a plane wave passing through a thin prism. Clearly, since the speed of the light wave is less in glass, the lower portion of the incoming wavefront, which travels in the emerging wavefront, as shown in the figure 10.9, which through the greatest thickness of light will get delayed, resulting in tilt in the emerging wavefront. In figure 10.7, we consider a plane wavefront and thin convex lens. The central part of the incident plane wave in uh, transversal to the thickest portion of the lens and is therefore and delayed the most. The emerging wavefront from the dispersion at the center, and therefore the wavefront becomes spherical and converges to a point F, which is also known as focus. In figure 10.7, see, the plane wave is incident on a concave mirror, and on reflection, we have a spherical wavefront converging at focus point F. In a similar manner, we can understand the refraction of light by concave lenses and concave mirrors. Okay, तो यहाँ से ये हमारा टेढ़ा हो गया, और ये जा रहा है तो यहाँ से जल्दी निकल गया, यहाँ से लेट निकला, यहाँ से और लेट निकला, ऐसे करते करते वेवफ्रंट बन गया। तो ऐसे ही मिरर है ना, हाँ, तो यहाँ से पहुँच के यहाँ जल्दी पहुँच गया, मेरे यहाँ पे इसको जाने में पहले देर लगी, फिर वापस आने में भी देर लगी, टोटल टाइम उसमें जाएगा। कूल। And monochromatic light is incident on a surface separating two medium. The reflected and refracted light both have the same frequency as the incident frequency. Explain why. हाँ तो यार ऊपर था तो सही, क्यों लैम्डा का होता है, न्यू तो कट जाता है हमारा, लैम्डा बाई वी होता है नहीं। When light travels in rarer to denser medium, the speed of light decreases. Does the reduction of speed imply a reduction in the energy carried by the wave? Nu energy is h nu, तो कहाँ ही depend करेगा। In the wave picture of light, intensity of the wave is determined by square of the amplitude of the wave. What determines the intensity of the light of the photon? ये पढ़ लेता हूँ. For a given frequency, intensity of the light of the photon is determined by the number of photons crossing a unit area per unit time. Coherent and incoherent addition of waves. In this section, we will discuss the interference pattern produced by superposition of two waves. ठीक है, चलो ऑलमोस्ट आधा हो गया. You may recall that we had discussed the superposition principle in chapter 14 of your class 11 textbook. Indeed, the entire field of the interference is based on superposition principles, according to which the particular point in the medium, the resultant displacement produced by a number of waves is vector sum of the displacements produced by each of the waves. Consider needle Consider needle S1 and S2 moving periodically up and down in an identical fashion and through water. They produce waves, and at a particular point, the phase difference in both the waves produced by each of the wave does not change. क्या? Both the waves at a particular point, the phase difference between the displacement happens when produced by each of does not change with time. When this happens, the two sources are said to be coherent. Figure 10.8 shows the position of crest solid circles and trough dash circles at a given instant of time, considering the point P from which the waves are originating. Okay. Since distances S1P and S2P are equal, waves from S1 and S2 will take same time to travel to the point P, and the waves that ema- emanate from S1 and S2 in phase will also arrive at point P in phase. Thus, if the displacement produced by the source S1 at point P is given by Y1 is equal to A cos omega t, then displacement produced by the source S2 at a given point will also be given by Y2 is equal to A cos omega t. Thus, the resultant of the displacement of uh, P would uh, P would be given by Y is equal to Y1 plus Y2, that is 2A cos omega t. Since the intensity of propagation intensity is proportional to the square of amplitude, the resultant intensity will be I naught is equal to 4 I naught. I is equal to 4 I naught, where I naught represents the intensity produced by each one of the individual sources I naught. I naught is proportional to a square. In fact, at any point, the perpendicular bisector of S1 and S2, the intensity will be 4 I naught. The two sources are said to be incoherent. The two sources said to interfere constructively, and we have what is referred to as constructive interference. What next considers that point Q? Here, point Q. S1 S2Q minus S1Q is equal to 2 lambda. A wave emitting from S1 will arrive exactly 2 cycles earlier than the wave from S2 and will again be in phase. Thus, if the displacement is produced by S1 is given by Y1 cos A omega t and Y2 is equal to A cos omega t minus 4 pi. That is again A cos omega t. Where we have the fact अभी सारा वही समझाया गया कि 2 lambda का डिफरेंस क्या होता है. Let's skip this one. Also, which corresponds to the condition. यहाँ से पढ़ते हैं. Now, if the two sources is coherent, that is, if the two needles are going up and down regularly, ये भी उसका एक part है. यहाँ से पढ़ते हैं. Interference of light waves and Young's experiment. That is YDSE. We will now discuss the interference using light waves. If we use two sodium lamps illuminating two pinholes, we will not absorb two interference fringes. This is because of the fact that light waves emitted from the boundary source, like a sodium lamp, undergoes abrupt phase changes in the time of order 10 to the power minus 10, independent of the source of the light. Independent of the source of light. will not have any fixed phase relationship and would be incoherent. When this happens, as discussed in the previous section, the intensity of the screen will add up. The British physicist Thomas Young used this ingenious technique to log the phases of waves emanating from S1 and S2. He made two pinholes S1 and S2 very close to each other and used an opaque screen. See figure 10.12a, ये वाला नहीं, ये तो 11 है ना, ये वाला पास में है ना, ठीक है। S1 and S2 higher. Then were illuminated by another pinhole that was in turn lit by a bright source. The light waves spread out from S and fall on both S1 and S2. S1 and S2 then behave like two coherent sources because light waves coming out from S1 and S2 are derived from same original source, and any abrupt phase changes in S1 will manifest in exactly similar phase, and S2 will be logged in the phase. That is, they will be coherent like two vibrating needles in water wave example. The spherical waves emanating from S1 and S2 will produce interference fringes on the screen GG dash as shown in the figure. The position of maximum and minimum intensities can be calculated by using the analysis in section 10.4 जो भी ऊपर use करा हमने. We will have constructed an interference resulting in the bright region when xd is equal to n lambda. Xd by capital D is equal to n lambda. That is, x is equal to xn is equal to n lambda d by d. इसको उधर भेज दिया, ठीक है. N is equal to 0 plus minus 1, that is n is equal to integer and belongs to z. On other hand, we will have destructive interference resulting in dark fringes when xd is equal to 2n plus half lambda. That is, x is equal to xn is equal to n plus 1 by 2 lambda d by d, where n can be any integer. Such dark and bright fringe bands appear on the screen, as shown in figure 10.13. Yeah, dark band हमारे 10.13 and 14 लिखा हुआ है इनमें. 14 कहाँ है पता नहीं. Thomas Young. Computer generated print pattern produced by 2 point sources S1 and S2 on the screen GG dash D is equal to 0.025 millimeter, D is equal to 5 centimeter, and lambda is equal to 5 into 10 power minus 5 centimeter. Okay, adopted from optics by A. Ghatak Tata, MC Grove, Hill published. जो भी है. Diffraction. If we look clearly at the shadow cast by an opaque object close to the region of the geometrical shadow, there is an alternate dark and bright region, just like the interference. This happens due to the phenomena of diffraction. Diffraction is general characteristic exhibited by all types of waves, uh, be it a sound wave, light wave, water wave, or matter wave. Since the wavelength of light is much smaller than the dimension of most obstacles, we do not encounter diffraction effect of light in everyday observation. However, the finite resolution of eye or an optical instrument, such as telescope or microscope, are limited due to the phenomena of diffraction. Indeed, the colors that we see on CD is viewed is due to the diffraction effect. We will discuss the phenomena of diffraction. The single slit. Okay, five more pages to go. In discussion of Young's experiment, we started with a single narrow slit act as a new source of the wavelight, uh, where the wavelight spreads from. Even before Young, earlier experimenters, including Newton, had noticed that light spreads out of the narrow hole and slit. It seems that the turn from the corner and enters the region where we could expect a shadow. These effect known as diffraction can only be the property understood using the wave idea. Oh, पहले इस चैप्टर की जो मुझे लगा हाईलाइट करने लायक है. After all, you are hardly surprised to hear sound. Sound is from someone talking around a corner. सही बात है. हमें तो नॉर्मल लगता है वो. When the double slit experiment in Young experiment is replaced by a single narrow slit illuminating a monochromatic source, a broad pattern with a central bright region is seen. On both sides, there are there are alternate dark and bright fringe regions. The intensity becomes weaker away from the center in figure 10.15. यहाँ पे बहुत dark है फिर कहाँ से आ रहा है? To understand this, go to figure 10.14. ठीक है. बोरिंग है यार ये चैप्टर बहुत. फिर घूम रहा है मेरा. Okay, let's resume. कहाँ पे था मैं? Figure 10.14. ये वाला. A straight line through M perpendicular to the slit plane meets the screen at C. We want the intensity of light at point P on the screen. As before, straight lines joining P to different points L, M, N. कहाँ है? अच्छा, P से L, M, N, etc. can be treated as parallel, making an angle theta with the normal MC. The basic idea is to divide the slit into much smaller parts and add the contribution at P with the proper phase differences. We are treating different parts of the wavefront at slits as secondary sources. Therefore, the incoming wavefronts is parallel to the plane of this slit. This source, uh, this source are in phase. These sources are in phase. It is observed that intensity has a central maximum at theta is equal to 0 and other secondary maximum at theta is equal to n plus 1 by 2 lambda a of lambda 2, which go on becoming weaker and weaker with increasing value of n. Minima is at n lambda by a. मतलब इसमें उल्टा हो जाता है जिसका जो पहले था उससे. चलो बढ़िया. The photograph and intensity pattern corresponding to it is shown in figure 10.13. There has been prolonged discussion about difference between interference and diffraction among scientists since the discovery of these phenomena. In this context, it is interesting to note that Richard Feynman has said his famous In his famous lecture of physics, no one has ever been able to define the difference between interference and diffraction satisfactorily. It is just a question of usage, and there is no specific important physical difference between them. The best we can do is, roughly speaking, is to say that when there is only a few sources, say two interfering sources, the result is usually called interference. But if there are a large number of them, uh, it seems that the word diffraction is more often used. In double slit experiment, we must note that the pattern on the screen is usually actually a superposition of single slit diffraction and each slit or hole from each little hole and the double slit interference pattern. ये एक्सपेरिमेंट है यार डबल स्लिट को देखने का, इसलिए मैं स्किप कर रहा हूँ. ठीक है, पोलराइजेशन पे चलते हैं. हाँ. Hmm. Polarization. Consider holding a long string that is held horizontal. The one end of which is assumed to be fixed. If we move the end of the string up and down in a periodic manner, we will generate a wave propagating in plus x direction. Such a wave could be described in following equation. Yxt is equal to a sin kx plus omega t. ये पढ़ रहा हूँ blue lines. The curve represents the displacement of the string at t is equal to 0 and t is equal to delta t. Representing when a sinusoidal wave is propagating in plus x direction, the curve B part, the curve represents the time variation of the displacement at x is equal to 0 when the sinusoidal wave is propagating in plus x direction. At x is equal to delta x, the time variation of the displacement will be slightly displaced from the right. Okay, where a and omega is equal to 2 pi v, 2 pi mu, represent the amplitude and angular frequency of the wave respectively. Further, lambda is equal to 2 pi by k. Lambda is equal to 2 pi by k. Represent the wavelength associated with further represents the wavelength associated with the wave. We had discussed propagation of such waves in chapter 14 of class 11 textbook. Since the displacement which is along y direction in the right side is at the right angles. भाई यार इसमें क्यों गलत पढ़ रहा हूँ मैं? Is at the right angles to the direction of propagation of waves. We have what is known as transverse wave. Also, since the displacement is in the y direction, it is often referred to as bipolarized wave. Since each point on the string moves on a straight line, the wave is also referred to as linearly polarized wave. Further, the string always remains confined to the xy plane and therefore it is also referred to as plane polarized wave. In a similar manner, we can consider the vibration of the string in the xz plane, generating the z polarized wave through displacement, which is given by zxt is equal to a sin x plus omega t. It should be mentioned that linearly polarized waves described in equation 10.15 and 10.17 are all transverse waves. That is, the displacement of each point on the string is always at right angle to the direction of propagation of the wave. Finally, if the plane of the vibration of the string is changed randomly in very short interval of time, then we have what is known as unpolarized wave. Thus, for an unpolarized wave, the displacement until the will be randomly changing when the time through it will always be with time, though it will always be perpendicular to the direction of propagation. कूल थोड़ा सा रहेगा। हम्म, कर लेते हैं अभी, पूरा लिखा होगा पेज पे। Light waves are transverse in nature. That is, the electric field associated with propagating light wave is always at right angles to the direction of propagation of light. This can be easily demonstrated using a simple Polaroid. We must have thin plastic-like sheets, which are made up of Polaroids. A Polaroid consists of long chain of molecules aligned in a particular direction. The electric vectors associated with the propagating light wave along the direction of the aligned molecules get absorbed. Thus, if an unpolarized light wave is incident on such a Polaroid, then the light wave will get linearly polarized, with the electric vector oscillating along a direction perpendicular to the aligned molecules. This direction is known as path axis of the Polaroid. Thus, if the light from an ordinary source like sodium lamp passes through a Polaroid P1, it is observed that its intensity reduces by half. Rotating P1 has no effect on the transmitted wave, and transmitted intensity remains constant. Now let an identical piece of Polaroid P2 be placed before P1. As expected, the light from the lamp is reduced in intensity on passing from P2 alone. But now rotating P1 has a dramatic effect on the light coming from P2. In one position, the intensity transmitted by P2 followed by P1 is nearly zero. When turned 90 degrees from this position, P1 transmits nearly full intensity emerging from P2. The experiment at figure 10.18 can easily be understood by assuming that 10.18 क्या? अच्छा मतलब पहले ऐसे था, फिर हल्का सा घुमाया, फिर पूरा घुमा दिया. Can easily be understood by assuming the light passing through a Polaroid P2 gets polarized along the path axis of P2. If the path axis of P2 makes an angle theta with the path axis of P1, then when the polarized beam passes through the Polaroid P2, the component E cos theta along the path axis P2 will pass through P2. Thus, as we rotate P1 or P2, the intensity will vary as I is equal to I naught cos square theta, where I naught is the intensity of the polarized light after after passing through P1. This is known as Malu's law. The above discussion shows that the intensity of the coming out single Polaroid is half the uh, incident intensity. By putting a second Polaroid, the intensity can be further controlled from 50% to 0% of the incident intensity by adjusting the angle between the path axes of two Polaroids. Polaroids can be used to control the intensity in sunglasses, video paints, etc. Polaroids are also used in photographic cameras and 3D movie cameras. And here we go. Wave optics भी खत्म. बस summary बस एक बार ये पढ़ देता हूँ. Passage of light through two Polaroids P2 and P1. The transmitted fraction falls from 1 to 0 as the angle between them varies from 0 to 90 degrees. Notice that the uh, light seen through a single Polaroid P1 does not vary with angle. B. Behavior of the electric vector when the light wave passes through two Polaroids. The transmitted polarization is a component parallel to the Polaroid axis. The double arrow shows the oscillation of electric vector. मतलब पहले ऐसे था, पास करके ऐसे ही आ गया क्योंकि 90 पे था, जब हमने घुमा दिया तो ऐसे आने वाला होगा सिर्फ. चलो, लेट्स एंड इट नाउ. तो कल हम लोग पी ब्लॉक करेंगे. हाँ, पी ब्लॉक के शुरू करेंगे. डिवीजन रिवीजन कह रहा हूँ, सॉरी, रीडिंग करेंगे. पी ब्लॉक में हम किस्तों में करेंगे, मतलब दो दो सेट्स के में करेंगे. 13 14 14 15 16 और 17 18 इन तीन सेट्स. तो अभी के लिए बाय बाय. कल दिन में करूँगा स्ट्रीम, देखता हूँ 10 11 बजे के आसपास.